So in this particular program for the JEE conditions, today we'll be discussing in the physics regarding the atoms. So atoms chapter comes under the modern physics conditions. Modern physics. So modern physics in the sense it is a combination of the atoms, nuclear physics, semiconductor physics, and communications. So as you can see in the previous examinations or the examinations which have been held in the February or the March sessions, you can see that there are at least some 5 questions are there from this particular chapters. Especially from the atoms, he is going to be concentrating on the Bose models things, De-Broglie's wavelength, De-Broglie's equations. So these are the main important things regarding this particular atoms. So here we'll be discussing some of the important topics regarding the atoms. So what are these important chapter topics? One is that this is an energy of an electron in an orbit and the emission radiation. That means whenever an electron jumps from an higher energy to the lower energy level, it's going to release some energy. And emission spectrum of hydrogen atoms. So this is the one. Another one is in de Broglie's exploration. So these are the three major important topics that we'll be discussing here today. Things. So first one, let me go for the Bose model of the hydrogen and hydrogen-like atoms and energy of an electron in this one. So coming to the electron in the orbit. So Bohr has assumed some of the assumptions regarding this particular that electrons will be revolving around the nucleus in an circular orbits. Okay, those orbits are called as your stationary orbits. So he has given a lot of assumptions. But for our derivations, we need a few things. So this is these are the circular orbits. Another one is an. He has also proposed that the angular momentum possessed by an electron in an orbit L is equal to, that is mvr, which is equal to the nh by 2 pi, where n is called as your nth orbit, nth Bohr's orbit, that is the radius, whether it's a ground state or first excited state or second excited state, like that. So as according to the Bohr's, at the center the nucleus will be there here. So around the nucleus there will be a stationary orbits in which the electrons will be revolving around the nucleus. So consider an electron which is there in the nucleus E, and nucleus is a positively charged one. Since this electron is moving in a circular orbit, it will possess a centripetal force. And that centripetal force can be written as n, that is mv square by r. This has been balanced, this has been equal to the electrostatic force between the positively charged nucleus and negatively charged electron. That will be the 1 by 4 pi epsilon naught into, that is Ze, which is a charge of the nucleus, and E, which is a charge of an electron, into distance is some r square. So now from this one, if I can get the value of the r is equal to, this is 1 by 4 pi epsilon naught into Ze square by, that will be your mv square. Okay, so instead of, for the given information, instead of this mv square, you can also replace with the kinetic energy can be replaced with the half mv square. Okay, so from this one, you can also replace this mv square with 2 times of the kinetic energy relations, please. Okay, so now when I substitute this particular value of the radius in the angular momentum, that is mv into 1 by 4 pi epsilon naught into Ze square by, this is mv square is equal to nh by 2 pi, we can find the velocity of the Bohr's orbit, nth Bohr's orbit. So from this relation, you can get the Vn is equal to, here the pi terms will be cancelled. This will be equal to the 2. So Vn is equal to, you can write it as n. So take the V to the other side, that will be the Ze square by 2 epsilon naught into nh. From this one, you can say that velocity of the nth orbit is proportional to the velocity of the nth orbit is proportional to the, this is Z by En. So these relations are very, very important regarding the Bose model and Bose model things, sir. So please be careful of this particular issues. Next one. So when I substitute this velocity in the radius relation here, we can find the radius of the nth orbit is going to be how much? The radius of the nth orbit can be obtained by the 1 by 4 pi epsilon naught. That will be your ZE square y. M into velocity of the nth orbit square, that will be Z square e to the power of 4 into 4 epsilon naught square into L square H square. So on removing the common terms or whatever may be the terms that are there, you can get the relationship between the radius of the nth orbit and the value of the z and the nth n value, which is the nth orbit. So this will be the n square into h square by this will be the pi m z e square. So that means your radius of the nth orbit is proportional to what, sir? N square by z. So based upon this one, you can calculate your kinetic energy here. So from this one, we can say that kinetic energy can be written as n. So how you can write the kinetic energy, sir, which is then half mv square. Okay, no, that will be your half mv square conditions, please. So half mv square, substitute the velocity in that particular. So you can substitute the velocity of the nth orbit in that particular equation of the half mv square, and accordingly you can find out the value of the energy relations in this particular case, please. So that is your energy relations can be obtained as on substituting this velocity here, please. So you can find out this energy is equal to, so that is your kinetic energy or anything, you can go for this one, please. So your kinetic energy, that is Ke of the nth orbit, is equal to 1 by 2 into m into, substitute your velocity over there, please. So that will be your z square e to the power of 4 by 4 epsilon naught square into n square, sorry, n to the power of 4. So sorry, n square into h square. So on replacing or solving this one, this will be the m into z square e to the power of 4 by 8 epsilon naught square into n square into h square. So that means your kinetic energy is proportional to the kinetic energy of the nth orbit is proportional to the z square by n square. So this is our relation. Since it's a bounded system, you can write the kinetic, that is the potential energy, is equal to negative of 2 times of the kinetic energy. Or potential energy by 2 is equal to kinetic energy. On solving this one, you will be getting the potential energy value as, that is minus of m into z square e to the power of 4 by, this will be the 4 epsilon naught square n square and h square. And your total energy will be numerically equal to the negative of the kinetic energy, and so that can be written as a minus m z square e to the power of 4 by 8 epsilon naught square into n square into h square. So this relation of the potential energy is equal to 2 times of the kinetic energy. You cannot use at any particular place. You can only use this relation in specific conditions only, specific situations only, that is for the bounded systems only you can use this relationship. So you cannot use in the case of the work power energy or general conservative cases, please. So these are the issues. Now from this one you can say that the energy is going to be related to the z square by n square conditions. From this you can find out the anything, that is the, well, as you know, the velocity and this one. So you can find the angular frequency, that is omega of the nth orbit, is nothing but an Vn by Rn. So since the velocity is going to be proportional to the Vn by Rn, when I substitute, or I'm just directly going for an z values and n values, so omega will be proportional to, here you have got the Vn, here you have got the Rn value. So that will be equal to your proportional to the z square by n cube. Okay, so here there is an n, here there is an n square, it will be proportional. Correspondingly, your frequency of the nth orbit is also proportional to the, correspondingly, your frequency is also proportional to the n z square by n cube only, whereas your time period is inversely proportional to the frequency, sir. So since the time period is inversely proportional to the frequency, so time period will be proportional to the n cube by z square. So please be careful. These are the very, very, very important relations. So please go through these relations, please. We might be doing the sums on the these things only. You might be doing the lot of questions are being asked not only in the mains but also in the advance. Also, these questions there will be number of questions asked on this particular concept. Okay, sir. So please be careful of this particular concept here, where you can find out the relations. He might be asking you the omega, he might be asking you the frequency, he might be asking you whatever may be the conditions, please. Okay, so these are your things. Suppose if you ask for the current relationship. So how does the current is been, that is electric current is been related to the charge? So where come here current has come down in this one? Since the electron is in the motion, it is moving in a circular path. So we can say that some electric current is also been there. Okay, so that electric current can be calculated as an I is equal. You can say that current I is equal to your number of, that is general formula. Ne by T, number of charges. Let the number of charges, one electron is there, 1 by T can be written as a time period, or you can go for the frequency into this one. So the current in the nth orbit is proportional to the frequency, so current will also be proportional to the z square by n cube relation. So you can also go for the magnetic field, where it will be inversely proportional to the n to the power of 5. Since it is a current moving in a circular coil, what is the formula for the current moving in a circular coil, sir? B is equal to, that is mu naught I by 2R. So from this relationship, you can go ahead for this one, please. So these are the very, very, very important things that you have to remember in this particular context, please. Now, since it's in an orbit, fine. So now, when we see this type of the question, here this is one of the important questions, that model questions that will be asked over here, please. So what he is asking, sir, here, imagine an electron is there. Imagine an electron in an hydrogen atom is replaced by a muon. Okay, you are replacing the electron with an muon. Mass of the muon he has given, that is mass of the muon is equal to some 207 times the mass of, times that of an electron. Okay, fine, we have got this relation. So electron charge and the muon charge of almost they are same. He is asking the ionization potential of the hydrogen is how much. So what is this ionization potential of the hydrogen? From where you can get this particular thing, sir? So these type of the questions will be very, very important over there, sir. So this ionization potential, or if you can go for the energy related things, please. So how is your energy and the mass are being, or the potential and the anything are being related? If we go for the earlier case, please, where your radius is inversely, here the mass of the electron is being replaced. So radius is inversely proportional to the mass. Okay. So energy is directly proportional to the mass here, please. So if radius is inversely proportional to the mass, how can I relate this radius to the ionizing potential, sir, here? So how can we relate this one to the ionizing potential here? So ionizing potential is nothing but an, sorry, yeah, this is the one. So ionizing potential, before going for the ionizing potential, I would like to write that radius is going to be or radius of the nth orbit is inversely proportional to the mass, sir. Radius of the nth orbit is inversely proportional to the mass since it's an hydrogen thing. So it will be proportional to the n square by z will be in the denominator. For an hydrogen one, that is z is going to be the one. So since they are being in the same orbit, so n doesn't have any important here. So this is the relationship. So that is Rn, radius of the nth orbit is inversely proportional to the mass here. So from this relationship, you can say that this is when I replace this particular thing, please. Or your ionizing potential will also be inversely proportional to the mass conditions. No, no. So when I replace that particular thing here, that is your acceleration part, that is a naught of an electron by a naught of the muon is equal to the proportional to the, because your acceleration is inversely proportional to the radius centripetal acceleration. This is r square v square by r. So I'm using that particular relation. This is mass of the muon by mass of an electron. Or from this one, this is AM is equal to AE by 207. So now on substituting, that is an acceleration of electron, that will be 5.29 into 10 to the power of minus 11 by 207. On solving this one, so you should be getting this one in terms of an electron volt. So these type of the questions will be asked over there. So coming to the next part of your emission radiation. What is this emission radiation thing? Whenever an electron jumps from an higher energy level to the lower energy level, okay, it releases certain energy. Suppose this is your ground state, n is equal to 1 when an electron jumps from the second state to the first state, or third state to the first state, or any other state to the ground state, or any other state, 3 to 2 also. It releases that energy, and that energy will be in the form of or photons, please. So we know that energy is photons are nothing but a bundle of the energies over there, please. So and that energy release generally it's a massless particles. So how can you calculate that particular energy? As in the earlier section we have written, in the earlier page, energy can be written as an m e to the power of 4 by, this is 8 epsilon naught square into n square into h square for an hydrogen like atom. So z is equal to 1. So on solving, on substituting every value into this one, in the sense, the mass of an electron, charge of an electron, epsilon naught values, and all these things, this energy will be written as n is equal to minus 30 total energy, basically 13.6 into generally z square by n square. I'm writing the generalized formula. In this session, we are taking an hydrogen, so z value will be equal to the 1. So if it is transition from some n plus 1th level to n level, in the sense the energy difference or the delta E can be calculated as from En it is transition to the En minus 1. So En value can be written as, and this is minus 13.6 into z square by n square minus of minus 13.6 into z square by n minus 1 whole square. Okay, sir. So, or else if I consider this n as an n1 and n minus 1 as some n2, then the same relation can be written as a minus 13.6 into z square by 1 by n1 square minus 1 by, sorry, n2 square minus 1 by n1 square. So, excuse me, I just here. So, this one should be your n1, and these are the things, please. Okay, thank you. So this should be your n2 and this should be your n1. So this is your n1 square. Now if I take the minus inside, 13.6 into z square of 1 by n1 square minus 1 by n2 square. This is your energy, the energy of a photon generally. So if I write the energy of the photon as an, we can write it as an h nu, difference in the energies, or this can be written as an hc by lambda. When I take everything on the other side and substitute, 1 by lambda can be written as an r of 1 by n1 square minus 1 by n2 square. So this is your emission energy, that is an energy which is being released whenever there is a transition of electrons from the higher energy states to the lower energy states, where R is called as your Rydberg's constant. R is called as an Rydberg's constant, and the value of this one is actually 1.09 into 10 to the power of 7. Okay, so or else you will be generally you can take it as a 1.1 into 10 to the power of 7. Okay, so your R value is nothing. R value is nothing but an it is a substitution of all these things, that is m e to the power of 4 by 8 epsilon naught square into 8 epsilon naught square into this is c into h square. Sorry, h cubed. So this entire thing is called as a Rydberg's constant. On substituting the mass of the electron and everything, you will be getting the same relationship. So this is how there will be an emission taking place over there. Now, so next question on this particular thing, which level of the singly ionized carbon has the same energy as the ground state of the hydrogen? Read the question carefully. He is asking which level, that means he is asking n value is how much, for whom, for the carbon, so that the energy of that nth state should be equal to the energy of the ground state of hydrogen. By the way, what is the energy of the ground state of the hydrogen? How can you calculate that one? Energy of the ground state of the hydrogen can be written as, and I'm going for the general formula, minus 13.6 into z square by n square here. Since it's an hydrogen, z value is equal to 1. And ground state, and because it's a ground state, so n value also 1. Then what is the energy of the ground state of the hydrogen will be equal to the minus 13.6. This I have written for hydrogen, sir. Okay. Now, when I go for the carbon, if I write the relation for the same thing, so the formula or the relation between the energy is going to be the same. Energy of the nth state is equal to minus 13.6 into z square by n square. According to the question, this energy is same to minus 13.6 electron volts is this one. So if I cancel these two things, what will happen? Your z square will be equal to the n square, or z is equal to n. What is the z value for the carbon? We know that z value for the carbon is equal to 6. So n value is also your 6. So this is the indication, sir. So like this, we can solve the sums there, please. Next one, emission spectrum, same thing in the hydrogen. There are the different types of the emission spectrums are there in the hydrogen. As I have written the basic formula, that is 1 by lambda is equal to R into 1 by n1 square minus 1 by n2 square. So coming to this particular case, there will be different energy levels over there, please. There are the different energy levels in an hydrogen atom. So in that one, if I go for the basic thing, so this is your ground state. If I take this as an, what is the number of the ground state? That is n is equal to 1. The energy of the ground state is minus 13.6 electron volts. It is minus 13.6 electron volts. Now, the next one, that is the first excited state, where the n value is equal to 2. The energy of the first excited state will be the minus 3.4. How can you get it, sir? By using the same relation, minus 13.6 into z square by n square, substitute n is equal to 2, that is 13.6 by 4, you'll be getting the same relationship. So next one, sir, where the n is equal to 3, that is your third excited n value 3, which is called as and your second excited state, or the value will be how much? Minus 1.51 electron volts. All these values are in electron volts only, sir. Okay. Now next excited state, if I go for the n is equal to 4, that is nth value, which is at fourth excited state, then the value will be minus 0.85, like that. So at every instant it will be decreasing. Now, what is the difference between the first excited state and the second excited state? This is the value you have to remember. 10.2 electron volts. Okay, sir, this is an energy which will be necessary for us to remember for solving the sums. And if an electron transition, or if there is a transition of charges from n is equal to 2 to first one, or n is equal to 3 to first one, or n is equal to 4 to first one, or from some infinite state to the n is equal to infinite state to the first one, n is equal to 5, I'll take up to the 5, sir, here. So what will be the energy of the fifth orbit? That will be minus 0.54. Okay, so these type of the series is 5 to 1 or infinity to the 1. So these, all of them are called as which sort of a series? They are called as an Lyman series. So they are called as your Lyman series. So when there is a transition from the higher energy levels to the first orbit, it is called as an your Lyman series. So first one I'm going, it is called as an Lyman. So that is 1 by lambda is equal to R into 1 by 1 square minus 1 by, it will be equal to the sum n2 square, where your n2 values will be changing from 2 comma 3 comma so on up to infinity. So generally this Lyman series comes under the UV region, that ultraviolet region. It will be of the region of ultraviolet region. Okay, so this is the speciality of the Lyman series. And your next case, that is your, you can go for the Balmer series. For the Balmer series, same relationship, 1 by lambda is equal to R into, but the transition has to take place to the second orbit. From the 3 to the second, from 4 to the second, from 5 to the second, like this. So you can have like this, there will be 1 by 2 square minus this one 1 by n2 square. So where you can take the n2 values starting from an 3 comma 4 comma 5 so on up to infinity. Where the Balmer series will be in the visible region, sir. Balmer series will be in the visible region. So like that, the third type of the series, you can take it as an Paschen series. So coming to the Paschen series, your first orbit, that is 1 by lambda, there will be a transition of charges from the higher orbits to only third orbit. You can call it as an Paschen series for this one. Okay, sir? Fine. This is called as your Paschen series conditions. Next one, sir. So, or this with where your n2 values for the Paschen series will be starting from an 4 comma 5 comma so on up to infinity, like this. Where the Paschen series comes under the infrared region. So it comes under this particular infrared region. So please be careful of this particular thing, sir. Okay, now. So now, so third one, we have completed. Your fourth type of the series is called as an, that is your bracket series. So coming to the bracket series, same relation, 1 by lambda is equal to R into, so any level to the fourth one, fourth level. Then that type of the series is called as a bracket series, where bracket series will also falls under the infrared region. So on your last type of the series, we can call it as an, that is your fifth type is called as an P fund. So in the P1 series, there will be a transition of electrons from any higher orbit to the fifth orbit. Then that type of the things are called as your fashion series, where the fashion series, where n values or your n2 values will come under the category of 6, 7, 8, so on up to infinity, sir. So Passion series will be far infrared regions. It will be under this region, please. So these are your emission spectrums of the any hydrogen atom where your Z value will be equal to the 1. Okay. Now, in solving these sums, so here in this case, he has asked jump from the n is equal to 2 to the n is equal to 1. So find the wavelength. We can use the standard relation 1 by lambda is equal to R into this is 1 by n1 square minus 1 by n2 square. I'm writing this relationship, please. I'm writing this particular relationship. Now n1 value will be substitute their corresponding things, sir. So that is R into 1 by 1 square minus 1 by 2 square, which is equal to the R value. If I take it as a 1.1 into 10 to the power of 7. Okay, no, sorry, minus 7. What I have written, sorry, please be careful of this one here. Okay, so sorry, right? 1 by R value, this is plus 7 only, right? So I'm just next this one 1 minus 1 by 4, that comes out to be the 3 by 4, 1.1 into 10 to the power of 7 into 3 by 4. So now lambda is equal to, which is 4 by 3 into 1.1 into 10 to the power of minus 7. So we need to solve for this one to get it into the nanometers. Nanometers in the sense 10 to the power of minus 9. It will be there. Obviously, you will be getting this one. So that is 4 by 3.3. When you solve, you will be getting the same sort of an information. So try to confine. Now, coming to the very important part. Whenever an electron jumps from its base level, electron comes to the base level from the immediate next level. That is, for example, Lyman series is there. Okay, for example, Lyman series, if an electron, its base orbit is 1. If electron jumps from the immediately next orbit to the base orbit, that is 2. If an electron comes from an n is equal to 2 to the n is equal to 1, then we call it as an longest wavelength. Then we call it as an longest wavelength. So this is the condition. If okay, this is the condition for this one, any case, or if there is a transition from n1 and n is from the n2 is from infinity, there is an electron which is coming from the infinity to its base orbit, then it is called as an shortest wavelength. So if you can remember, if you try to remember these values, it will be great, comfortable. Or else you can solve this one. So the questions have been asked on this particular concept, or to find out the what is the longest wavelength, or to find out what is the shortest wavelength, like that. Okay, no. So the longest wavelength of the Lyman series will be somewhere around 6,500 angstroms. It will be, and the shortest wavelength is going to be say even more less than that particular thing. So due to that reason, the Lyman series is being considered in an ultraviolet region, where violet wavelength is of, or the lambda of the violet is 3,800 angstroms, or for our remembrance you can take it as an 4,000 angstroms. So the Lyman series lies around this wavelength of the violet, so you can call it as an ultraviolet thing. So that is the reason for this one. Next one. So coming to this one, De-Broglie's explanation of the Bose model. What does the De-Broglie has explained? According to the De-Broglie's hypothesis, the photon or the powder or the massless particle is there. It is of the wave nature as well as an particle nature. And he has proposed by the Einstein's relation, that is E is equal to mc square, and Planck's relation E is equal to hc by lambda. The energy will be same in this sense, which is mc square is equal to hc by lambda, or your lambda is equal to h by mc. This is the velocity of the light, or if any particle travels with the velocity less than the velocity of the light or some other value, then this will be your de Broglie's wavelength, which is h by mv, where mv is called as an momentum. So according to the de Broglie's wavelength, so lambda can be written as an h by momentum, where h is called as in Planck's constant, that is equal to the mv, or you can also equate to the some small p. Momentum is been represented by the small p. So whilst it's a very easy concept, but please be careful in applying the de Broglie's wavelength. So why it is easy means the formula or the conversion of the formula will be same. For example, he has asked you to find the wavelength of the electron or a particle which is moving in an which is moving with an some kinetic energy. If he says some kinetic energy, that means he has not given the information of the momentum or the mass or velocity. He has not given any such information here, please. He has given the information in terms of the kinetic energy. So you need to convert the de Broglie's wavelength in terms of the kinetic energy. We know that kinetic energy Ke is equal to p square by 2m momentum square by mass. From this one, momentum can be replaced by root over, that is 2m into kinetic energy. So use this relation if he mentions about kinetic energy in the question. Or if he mentions only about the velocity or the mass, we can go for the standard equation lambda is equal to h by mv. If he mentions about the kinetic energy, please only convert the basic formula into the kinetic energy terms. Or else, if he mentions about the potential, so potential is V. We know that kinetic energy is equal to potential into charge. So that means the lambda can also be replaced by h by root over 2m into potential into charge. So if he asks about the potential, you have to convert this in terms of this potential conditions, please. Okay, or else the potential can also be replaced by V is equal to ED, that is the potential into electric field into distance. You can also replace this particular thing. So depend upon the parameters that are being given in the question, you have to convert your basic formula, that is lambda is equal to h by mv, into the given format. So this type of the things is very important. You have to be perfect with conversion of the basic formula of the de Broglie's wavelength into the given parameters. So if you can do that, this de Broglie's explanation or the de Broglie solving of the sums on the de Broglie's wavelength will be very easy. So please be careful of this one, Anna. So next one. So what can be the sum on this one? The particle is traveling 4 times as faster as electron. That means velocity of the particle is equal to 4 times the velocity of the electron. This is the information he has given. Assuming the de Broglie wavelengths of the particle and electron until lambda of the particle by lambda of the electron is equal to 2 is to 1. The mass of the particle is how much he is asking. So how can you find the mass of the particle? As you know, the de Broglie's wavelength, lambda is equal to h by mass into velocity. Lambda is equal to h by mass into velocity. So here mass and he has given the velocity since it is constant. So he is asking the de Broglie, assume the ratio of the de Broglie's wavelength of the particles also he has given. So this is lambda of the particle, mass of the particle, velocity of the particle. Lambda of the electron is equal to h by mass of the electron, velocity of the electron. Now, particle to electron ratio, that is lambda p by lambda e, is equal to 2 is to 1. When we put down the ratio of these two things, please, h by mass of the particle and these things, then what will be left over there? Mass of the electron into velocity of the electron by mass of the particle into velocity of the particle. What is the ratio of these two things? Velocity of the electron by velocity of the particle from here. Electron by particle is 1 by 4 now. Substitute over there. Mass of the electron by Mass of the particles, please. Okay. This is equal to into 1 by 4 I am writing. So that is equal to the, as I multiply this one, 4 into 2 will be the 8 by 1 is equal to mass of the electron by mass of the particle. So he is asking the same relationship. Mass of the particle is equal to 1 by 8 times of the mass of the electron. Right, sir? So this is the what he is asking. So these type of the questions, please. Now, as we came to the end to this one, these type of the questions, whether the questions concern in depth or the questions which will be very very useful for you for applying the or appearing for the JEE mains, there are a lot of interesting questions or creative questions which are being provided in our website or in our the app. So you can subscribe to solve those sums so that you can get perfection in this particular chapter. And for subscription, if you can use the promo code JJ10, then the 10% of the amount will be discounted on your total amount when you use this particular promo code. Right? So thank you. Next in this one, please. Hope you will be considering this one and utilize the services used by the RISE. Now coming here, these are some of the questions you have to solve. Can you try it out, please? Yes, ma'am. So now I'll solve this one. What is the question given here? De Broglie wavelength he has given associated with an electron and a proton are calculated by an accelerating potential he has given. Potential difference is same. What should be the ratio of the wavelengths he is asking? That means which relation you have to use? You have to use the relation between the wavelength and the potential. So which is h by root over 2m into potential into charge. So when I go for the ratio lambda of the electron by lambda of the proton is equal to, obviously h terms will be cancelled. So I'm directly writing root over mass of the proton potential into charge of the proton by 2 into mass of the electron into potential of the electron into charge of an electron. Now, obviously all the terms will be cancelled. The leftover term is going to be the mass of the proton by mass of the electron. What is the mass of the proton is 1.67 into 10 to the power of or minus 27 kgs by 9.1 into 10 to the power of minus 31 kgs. So when you solve these two things, obviously you should be getting the lambda 1 by lambda 2. The de Broglie's wavelength should be in this particular ratio, sir. So please be careful of solving this one. Next one, an alpha particle and a proton are accelerated through the same potential difference. Again, here also, he has asked in the same potential difference. So lambda is equal to, you should be now adjusted to the formula of the potential, which is h by root over 2m into potential into charge. So from this one, lambda of the proton by lambda of the alpha is equal to h term will be cancelled. So that will be the under root of 2m alpha into potential into charge of alpha by 2m into this one is proton into velocity of the proton into, is there any other factors are here, into charge of the proton. So what is an alpha charge and the proton charge? If proton charge is, if charge of or E of the proton is equal to 1, then E of alpha is equal to 4. Okay, sorry, 2 times of the charge of this one, whereas the mass will be 4 times. So like that you can substitute and the potential will be same almost. Because alpha is, the proton, alpha particle and proton are accelerated from the rest under the potential difference of 200 volts. So now how to solve this one, sir? Root over. So mass ratios, sir, what are the same? Under the same potential difference. What do you mean by under same potential difference? V can be removed. Charges ratio asked only. This will be what ratio, sir? Masses ratio. Mass of the alpha particle 4 is 2 into. So now when you solve this one, 2 will be cancelled. That ratio will be the 2. So these type of the simple questions will be there. Now, when the following transitions of the hydrogen-like atom of the frequency emitted by the photon is maximum, when it will be there? So frequency is maximum. Energy can be related as the h into frequency now. When frequency is maximum, that means energy is also maximum. So for which transition you can have the more energy, sir? For which transition you can have the more energy? If you read the theory properly, this will be sufficient. This you can answer easily. Here you can see here spectral lines I have drawn here. Look at here. This is the energy which is released maximum when there is a transition from second orbit to the first orbit. So that is a very point that we need to remember. So that point already I have mentioned. That means when there is a transition from n is equal to 2 to n is equal to 1, how much energy is released? 10.2 electron volts of energy will be released. Got it, Nana? Next one. So with the de Broglie wavelengths of the alpha particle and the proton are equal. That means lambda of the alpha is equal to lambda of the proton. Then the ratio of their velocities is asking. Can I replace this one? This is h by mass of the alpha into velocity of the alpha is equal to h by mass of the proton into velocity of the proton. H terms can be removed here from this one. Mass of the, he is asking, mass of the alpha by mass of the proton is equal to velocity of the proton by velocity of the alpha particle. So what will be the ratio here, please? He is asking ratio of their velocities is equal to their ratio of their masses. Mass of the alpha, if I take it as a 4, mass of the proton will be 2. So velocity of the proton by velocity of the alpha will be equal to the 2 is equal to velocity of the proton by, sorry, velocity of the alpha by velocity of the proton. Got it? So this is how you can solve the sums. Now next one, the energy required to remove the electron in a singly ionized helium is 2.2 times the energy required to remove an electron from the helium atom. The total energy required to ionize the helium atom completely is how much? So most probably should be 109 electron volts. How do you get it, sir? So energy required to singly ionized helium, energy formula minus 13.6 into Z square by N square. So where your Z value for the helium will be 2 obviously. Remove an electron here is equal to is how many times? 2.2 times the energy required to remove an electron from the helium. Okay, now. So singly ionized hydrogen means this is the one. So one, sir. So minus this will be minus 13.6 electron volts will be there, and this is equal to the doubly ionized helium, sir, which is minus 13.6 into Z square by, that is 2 square by n value enta. What can be the n value? Remove an electron, sir. He is asking to remove energy required to remove an electron from the helium atom. That is, n value can be 1 here. So he is asking the total I required to ionize. So the total energy required for the ionize, calculate and substitute all these values. You can get the total energy required for the ionization conditions, please. So what is this? 13.6 into 4 times is? Yes, Nana. So 13.6 into 4, you need to multiply and verify whether you are getting the correct answer or not. So these are the certain examples that we have done here. So please be careful, read properly. It's a very, 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 very important concept here where we can expect at least 1 or 2 questions from this particular chapters or from this particular concepts. Okay, so don't neglect it. Do as many sums you can do it. Do as many sums you can do it. Okay, now, and use for having the more number of the sums. Please go for the subscription. For every subscription, you can use this promo code that is JJ10. You can get the 10% subscription on whatever the months you are going to take it. So, which will be very useful for the practicing session. Got it, sir? So, this is a very important, very important formulas or very important topic that we have studied today. So, what are the important topics that we have studied? Relations between the physical quantities and their nth orbit, that is L relationship. Okay, so these all these the whatever the relations, that is 1 by lambda terms, lambda relations, energy transition questions, energy questions. So all these are very important thing, please. So here we have in the first page we have obtained the relationship between the radius and nth orbit and as well as z. So in the other cases also we have described the relationship between the time period and the n value and z and magnetic field also n value and the z we have described the relations. So these relations please try to remember them. It is because it's difficult or not difficult, it will be a time consuming process for you to do this derivation in the examination and obtain the values over there. Okay, so that is the main problem. Fine, sir. So now with this, me, Jairam, that is physics faculty, closing the this session of atoms from the rise.